Hello everyone and welcome back. In this video we're going to be exploring integral calculus but using a software that is free to use online known as Desmos and how we can use Desmos to do some of the common integral calculations just in case you 1. Don't know calculus yourself, 2. You do know calculus but you don't want to work through say the analytical computations, possibly you want just a approximation or a numerical representation of your answer. If you fall into either of those categories, then Desmos is definitely a great tool to use. And even if you do know calculus, sometimes using Desmos as a calculator is sometimes useful to get maybe some upfront insight on the problem that you're looking at. So let's just look at a quick problem. Let us assume we have a function f of x which is equal to sine squared x plus cosine x. So if you remember from pre-calculus, sine squared is an even function, cosine is also an even function. So when you add two even functions, you also get an even function back. So if you were to look at the graph of this function f, then you should have the graph of some symmetric function that is symmetric with respect to the y-axis. And indeed, this function is one of those properties because the function actually looks something like this. So one should be able to see that there at least on this graphed domain exist two maximum values, which are there. One can find that those are exactly equal to negative pi over 3 and pi over 3. So one of the questions that integral calculus is interested in is, for example, the area under the curve on a specified interval. So of course this is a symmetric region, so one may ask, well, what is the area under the curve from minus pi over 3 to pi over 3? That is, what is that area equal to, at least approximately, if you don't know how to do calculus. So from the calculus notation perspective, that area A can be found by doing the integral from minus pi over 3, the lower bound, to pi over 3, the upper bound of the function that we are integrating, of sine squared x plus cosine x, and then we also have this differential dx. Now, if you're not familiar with what integrals represent, you can sort of think of this as an infinite sum of rectangles, because we can always approximate the area under this curve using some rectangles. For example, we can do, that rectangle, that rectangle, that rectangle, that rectangle, that rectangle, that rectangle, and that rectangle, right? So this little symbol practically represents an infinite sum. This represents the height of each of those curves, and this dx sort of corresponds to the length of each of those boxes, where that length is infinitesimally small. Now, if you do know calculus, you should be able to show that this integral is equal to exactly 3 square roots of 3 divided by 4 plus pi over 3. Now, let's assume that you don't know how to get that answer, but you need a numerical approximation to that. That is, as a decimal, what is this approximately equal to if you don't know the exact formulation of that? So, of course, one should be also familiar with the fact, and if not, that's okay, that this integral, a, which is equal to the integral from, say, a to b, where a is the lower bound and b is the upper bound, of f of x dx, can also be calculated via the integral from a to b of f of t dt. That is, it doesn't really matter what this variable is, as long as the variables of those things match, then the answers will be exactly the same exact thing. The only reason I mention this is because this is actually going to be a preferred method in the Desmos world and also several other numerical calculating packages, because usually we define functions in terms of x, and we don't want to use that variable for calculations if we're not going to be using that variable for something else. So now that we have the basics of integral calculus, let's jump into Desmos and see how we can solve these problems and several others. So here we are in the Desmos world, which you can navigate to easily by going to www.desmos.com/calculator. So the first thing that I want to do is define the function that I want to do calculus on. So the function that we were defining before was sine squared x, and you can get the squared or any exponent via the little shift 6 caret key looking symbol, and then we had a plus cosine x there. So here is our function that I sort of sketched on paper before. Now, if you want to restrict the domain in Desmos for graphical purposes only, you can do a curly open brace, do minus pi over 3, and then less than x less than pi over 3 for the upper bound, and that will graph the interval for which you are interested in. Of course, maybe you want to go out a little bit more. For example, you can go to minus pi to pi, and that will graph a larger region if you're interested in that. So the problem that we were interested in is finding the area under the curve of f from minus pi over 3 to pi over 3. You can easily sketch that region as the shaded region in Desmos very easily. You can do 0 less than y less than our function, and then specify the interval for which you're interested in calculating. For example, we wanted minus pi over 3 to x to pi over 3. So we want the shaded area of this blue region shown in this diagram. So in case we want to find that, we can easily do so. So we can do the integral from minus pi over 3 to pi over 3 of our function f of x dx, and that will give us our approximate answer. Now remember, you could also do this doing f of t dt, and you should get the same exact answer. In fact, you should be able to get the same answer regardless of the variable you use. So you could do f of theta d theta, f of y dy, f of z squared dz squared. Technically anything will give you the same exact answer, which is actually pretty nice. So is that the same exact number that I specified before? So we can try that. So 3 square root of 3 divided by 4 plus pi over 3 does in fact give us the same exact solution, for which I at least conjectured was the answer before. So those are some of the basics of integral calculus in Desmos. Now, in case you're familiar with, for example, indefinite integrals where the lower or upper bounds can be positive or negative infinity, Desmos can easily do that. So for example, let us assume we want to do the integral. So in case you don't know how to do the integral in Desmos, it's I, n, and once you press t, the integral will pop up. Let's assume we want the integral from 0 to infinity. So to type in infinity, it's infty, and once the y is typed, the infinity will come up. And let's assume we want to find the integral from 0 to infinity of sine t. So sine t times e to the minus 2t dt, and we have 0.2, which is the same as 1/5. So what exactly does this curve correspond to? Well, you can graph it. For example, y is equal to sine of x times e to the minus 2x, and that's going to be this curve shown in red. So it's practically the integral, or the area, 0 less than y less than, let's call that, say, g of x. Just to give it a name so we can start shading it if we want to. So it's the area of that blue region. So, most of the area appears to be from 0 to say 3, but technically there's really small area from 3 to infinity, so that definitely does count. So that is the area from 0 to infinity of this particular curve. That integral, of course, has several other meanings and applications, which we're not going to get into today, but if you've heard of Laplace transforms, then this integral should look very familiar as well, and that should also give you some tools on how to prove without Desmos that that actually is equal to 1/5. Now there's several other integrals that you may want to explore. For example, the integral from minus infinity to infinity of 1 divided by the square root. So if you want to do square root, it's SQRT of 2 pi. If you want to do pi, it's pi. And then times e to the minus 1/2 t squared in the exponent dt. Now notice that we get a very beautiful number, in particular 1, right? So what exactly is this curve and what does it look like? So if we type in h of x, and that's going to be equal to this function that I've defined here. Let's change that to x so it can graph. It'll also graph with t, but nonetheless, that's pretty much what we're looking at. So that's the graph of this curve. Now, it might not look familiar on this particular scale. You can actually change the scale very easily. For example, let's go from negative 3.5 to 3.5 on the x-axis. And for the vertical axis, let's go from negative 0.1 and let's go up to 0.6. Now, from this scale, does this curve look familiar? It should, because this is what we call the standard normal distribution, which has several different applications in probability and statistics, right? And one of the properties of probability is that the area under this curve, which is 0 less than y less than h of x, this area shaded in black should be equal to 1, and at least Desmos does agree with that property. That is, this curve is a probability density function for some random variable x, right? So as you should already know, probability is one of the easiest or first good applications of integral calculus. So those are some of the basics of integrals and indefinite integrals, also how to restrict domains, draw some shadings, and just evaluate integrals overall. Now let us look at a couple special integral calculus concepts that you probably will if you have not already encountered in your study of integral calculus. One of the important functions that are defined in terms of integrals is what is known as the gamma function. So the gamma function, which is written as capital gamma of x, is equal to the integral from 0 to infinity of t to the x minus 1 e to the minus t dt. And usually we define this curve on the interval x on 0 to infinity, right? So if you were to graph this curve would look something like that. So it's a convex function. It's monotonically increasing after some unique minimum value there. So one of the properties of the gamma function that you may not know is that gamma of x is equal to x minus 1 factorial if and only if x is a natural number. For example, 1, 2, 3, 4, up to, say, infinity, and of course 0 factorial, which is the same as gamma 1, will be equal to 1 by definition. At least from the factorial, that's a definition, but that actually is true from this definition. Now, one may ask, well, how do I evaluate the gamma function by hand if I want to? So using this property, one should be able to show that, for example, gamma of 4 is the same as 4 minus 1, or 3 factorial, which is 3 times 2 times 1, which is equal to 6. And say gamma of 6 is going to be equal to 5 factorial, which is going to be 5 times 4 times 3 times 2 times 1, which is the same as 20 times 6, which is the same as 120. Now, of course, since it's defined on 0 to infinity, we can evaluate the gamma function at infinitely many numbers. For example, one may ask, well, how do you evaluate gamma of 1/2? Right? So some people will say that this is equal to negative 1/2 factorial, but this notation very, very bad because naturally the factorial is only defined on the natural numbers n 0. Of course, you can analytically extend factorials via the gamma function, but that does not mean that negative 1/2 factorial equals gamma of 1/2. Negative 1/2 factorial can be equal to other things besides gamma of 1/2 if you extend it in different ways, right? So if you see any people write like fractions or decimal factorials, that's just abusive notation, so definitely be aware of that. Now, gamma of 1/2 does exist in isolation, and one, if you are familiar with, say, multiple integrals or polar coordinates, it's a nice, fun little exercise to show that this is actually equal to the square root of pi. And you could also show, for example, that the gamma of 5/2 is equal to 3 square root of pi divided by 4. There are several other values for which gamma can be evaluated, and you can have a closed form that involves such as square root of pi, but there's also infinitely values, at least by the time of me making this video, does not have closed form representations that we currently do know so far. So for example, if I ask you, what is the gamma of pi divided by e? At least at this time, there doesn't exist a pretty form of that, so we need a numerical approximation for that. So Desmos, of course, can do gamma functions. Let's go ahead and see how Desmos deals with these types of things. In the natural form of Desmos, there doesn't exist any capital Greek letters besides your basic ones that are encountered. But for all of the Greek letters that are capitalized, Desmos doesn't, at least currently, have all of those implemented. But there does exist some extensions where you can actually type, for example, a capital Gamma, and the capital Gamma symbol comes up. But if you don't have that extension installed, that's okay. You can use capital G of X just to represent the gamma function, at least temporarily. As long as you know what capital G stands for in terms of the gamma function, then all is well. But I'm going to be using the formal representation gamma of X just so that there is not any confusion. So you can define the gamma function in terms of its indefinite integral form, in particular the integral from 0 to infinity of t to the power x minus 1 e to the minus t dt, and it will eventually graph it, right? So as you clearly see, here is my gamma function, and there is its unique minimum located at x is equal to 1.4262. Now, if you work with the gamma function a lot in a lot of computations, it may be a little bit slow. But since gamma function is such a popular function, Desmos actually already has this implemented in its software. It actually has it implemented, in particular, as x minus 1 factorial. So if you type x minus 1 factorial, and let's just look at just the right-hand side, in particular x is greater than 0, just to not cause any confusion, that does actually produce the gamma function, and I think that way is very, very easy in terms of its implementation. So for example, if I ask you, what is gamma of 1/2, it gives you approximately equal to 1.7725. So is that equal to the square root of pi? Indeed it is, right? But of course, Desmos will not give you analytical values or exact values. It will just give you approximations. But if you don't care about the exact value, Desmos will serve your needs. So for example, I can do gamma of 5/2, which we already know the exact value of, and that gives you 1.3293. And you can evaluate this at all of the other values, even if you don't know the exact value, or maybe it doesn't exist at the time. For example, pi divided by e, that will give you 0.9311. Now there are some other functions that are related to the gamma function, for example the beta function. So the beta function bxy is defined to be equal to gamma x times gamma y divided by gamma x plus y. Now this is of course a multivariable integral function, which we're not really going to get into. Or it's a multivariable integral function, yeah. We're not going to get into it at least now, but later it does have several applications in a variety of fields. But I just want to mention it now because it's a nice little extension of gamma. So if I ask you, what is beta of 2.1 as x and 3.2 as y, it will give you that particular value. So that's just a brief introduction to the gamma function and beta function if you haven't already encountered it, but maybe you will see it in, say, probability theory, where it definitely does have its immediate applications in a variety of different fields. So at least even if we do not know calculus, you can use Desmos to calculate their values. As I already mentioned so far, probability is one of the easiest or familiar applications associated with integral calculus, at least on the pure side of things. So let's look at an example of how we would deal, for example, with probability theory in case your focus is targeted in that direction, or you're curious how to do probability theory or continuous probability theory in Desmos in case you are not comfortable, for example, with all the theoretical things and the analytical things, and you just want to calculate answers, for example, for applied reasons. So what I'm going to do is I'm going to define two numbers, which you'll see what they are in a moment. So a is equal to 2.9. Let's let b be equal to 1.7. And let's define our gamma function again. So gamma of x equals x minus 1 quantity factorial. Let's ignore its graph because that's not going to be our primary focus. We're just going to be using that function. So what we're going to do is we're going to do f of x is equal to, and on the top we're going to do gamma a plus b. On the bottom we're going to do gamma of a and then gamma of b. So that's obviously the reciprocal of the beta function of ab. And then we're going to have times x to the a minus 1 and then times 1 minus x to the power of b minus 1. And notice that this curve is only defined on the interval 0 to 1. So let's scale our graph out a little bit. So our lower bound, let's make that say negative 0.1, and the upper bound, let's make that 1.1. And that's a good curve. So notice that most of our distribution is definitely to the right of 0.5, so this is definitely a skewed left function, right? So the first question that you may ask is, and you can put quotes in Desmos by just doing a double quote here, and then it'll switch to quote form. So one could ask, is this a probability density function? The answer is yes, if and only if the area under this curve from 0 to 1, so 0 less than y less than f of x, the area of this blue shaded region, if this area is equal to 1, this is a probability density function because obviously it's above the x-axis, so that property is satisfied. So life will be wonderful if that is. So we can easily calculate integrals up to this point, right? So the integral from 0 to 1 of f of t dt, is it equal to 1? Yes, therefore yes, it is a PDF. Yes, smiley face. So since it is a PDF, then you should be able to calculate the expected value or the mean of that distribution. So I'm going to do E sub x, so that's going to be the expected value of x. So if you're familiar with probability theory, then you should know how to find the expected value, at least theoretically. But if you don't, you can do the integral across the domain of your density function, variable times probability density function dt. So the mean of this distribution is 0.63. The second moment, which is a measure of variation, I'm going to call it E sub x2. That's going to be equal to the integral across the domain of t squared times f of t dt. That's going to be 0.44. The use for this is going to be to calculate the variance. So variance of x is going to be equal to the second moment minus the mean squared. So the variance is equal to that, and the standard deviation, which I'm going to call Sx, that's just going to be equal to the square root of the variance, right? So the standard deviation is 0.20. And there's several applications associated to expected values, second moment variance, and standard deviation, but that's how you can calculate each of them in Desmos. So another calculation or set of calculations that you may want to do in Desmos is percentiles. So in order to calculate percentiles, the easiest way would be to calculate its cumulative density function. Cumulative density function, or CDF for short. CDF. So we're going to represent the cumulative density function for little f by capital F, and this is going to be equal to the integral from the lower bound of the domain up to x of our curve f of t dt. So as all of you should already know, if this blue curve represents our probability density function, then it should be an always increasing function, and it should start at 0 and end at 1 at the tail of the domain, which this definitely does. So what if I ask you to find the median of this distribution? So if I graph y is equal to 0.5, which corresponds to 50%, and find where that line crosses this curve, we see that 0.65 is the median of this distribution. That means 50% of the data lies to the left of 0.65 and 50% of the data lies to the right of 0.65. So if I want to get that exact value and store it, then I can do 0.50 tilde and then f of the name of the variable that you want to assign its value. So since the 50th percentile is the median, I'm going to call this capital M sub x. Therefore, it's going to store the answer 0.6507 into your answer. So that is going to give us the median of this value, and then you can do anything with calculations with this number if you desire so. So that's how you calculate the 50th percentile. But what if you want another percentile? So any percentile at all that you want. So 0 to 100%. So if I want the 72nd percentile of this distribution, I would do 0.72 tilde, the cumulative density function, then the variable for which I want to name the 70th percentile. So I'm going to call it x sub 70. Okay, so the 72nd percentile is going to be 0.78. So 72% of the data lies to the left of x72, and 28% of the data lies to the right of the 72nd percentile. And that's the basics associated to single variable probability theory in Desmos. Although a lot of problems can be simplified to single variable probability theory, most practical applications definitely involve more than one variable, which of course introduces the concept of multivariate probability theory. Although we're in the middle of a single variable calculus discussion, it might be useful to at least expose yourself to the idea of multivariable or multivariate probability. So let's assume that we have a multivariable, in particular two-variable function. Let's call this function gxy is equal to 2x squared plus 4y squared. So this is not a curve in two-dimensional space. This is, of course, a surface in 3D space. Okay, so we have an x-axis, a y-axis, and then a gxy axis. So of course we have some surface floating above this particular region. So let's assume that we choose a cross section. So let's assume that this corresponds to some point. So that's the cross section. Let's call that x1 and let's call that y1. I think I've reversed my axes, but that's okay. Let's call that x1, let's call that y1, and let's assume that this up here is, say, x2. Let's call this point y2, and of course that corresponds to the other region as well. Right, so we have a projection down to the floor that corresponds to some sort of rectangular domain. Right, so let's assume that the domain of definition is equal to x1, x2, comma, y1, y2, right? So some rectangular domain. And one can ask, well, is the volume under the surface on this two-dimensional region equal to 1? If it is, then that means this two-dimensional curve is a probability, in particular a joint probability density function for two variables, x and y. So that is, we want to know, is the integral from x1 to x2 of the integral from y1 to y2 of gxy dy dx. Keep in mind the order of integration matters here. And we want to know, is this equal to 1? Right? So of course, if you definitely don't know single variable calculus, then multivariable calculus may seem intimidating, but Desmos actually does deal with multiple integrals very well. So let's see if we can deal with multivariable probability theory in Desmos, at least to some degree for the basics of the analysis. So let's see how that looks. So the first thing that we need to do is to define our multivariable function in Desmos. So we defined it as gxy is equal to 2x squared plus 4y squared, right? And let's just take note of the domain that we want to work with. Let's assume that the domain is x in, let's call it 0 to 1, and let's assume y is in 0 to 2. Let's assume that that is the domain we want to play in. Okay, so we want to know, is the volume under the surface equal to 1? Of course, this is a two-dimensional graph, and the base package of Desmos Calculator doesn't have 3D, but it does have some other 3D features in other parts of the platform. You can investigate that and explore if you're interested. Okay, so let's just focus on the numerical side of things. So let's look at the volume under the surface. Let's call the volume equal to A. I know it's not area, but I want to reserve, for example, V to be equal to the variance of that variable. So A is going to be equal to the integral from 0 to 1, so that's going to be my x integral, and then I want to do the integral from 0 to 2, that's going to be my y integral, and then I'm going to do GAB, so those are my dummy variables, dB for y, and then dA for x. So the area or volume under the surface is equal to 12. Therefore, is G a probability density function for x and y? No, because that should be equal to 1. Now we should be able to build a probability density function from G by normalizing or shrinking down that area. Because if I divide both sides of this integral by 12, then I have that normalized area is now equal to 1. So if I look at a new function, for example fxy, which is going to be equal to 1 over that area, and then I'm going to do, for example, gxy, and then I do the integral of this new function, then the volume under that surface ideally should be 1. So let's take a look at that and actually see if it is. So the integral from 0 to 1, and then the integral from 0 to 2 of this new function, let's do f of a comma. Now we can't do a and b anymore because we're already using it here, and we've used a in that definition of f, right? Therefore we have to change the variables here a bit. So that's going to be st, and then t is our dummy variable for y, so it's going to be dt, and then ds. right? So notice that the volume under this surface F is equal to 1. Therefore, F is a probability density function for variables x and y. So that's really, really nice. So in case you're not familiar with multivariable probability theory, a useful way to analyze the variables x and y in isolation is to look at what we call the marginal probability functions. So the marginal function for x, which I'm going to denote as f sub x of x, is going to be equal to the integral along the y domain. So the integral from 0 to... So what is the y domain? It goes from 0 to 2. So I'm going to integrate from 0 to 2 of f of x, and then I'm integrating with respect to the y variable only. So I'm going to call that f of xt dt, right? So notice that this is a function of x only, not x and y, so it does attempt to graph that particular marginal probability function. And you should be able to show that the integral from 0 to 1 of fx of s ds is equal to 1. So marginal probability functions are also univariate probability distribution functions. That's, of course, a nice little theorem to prove in case you are in the realm of probability theory. Now let's look at the marginal probability function for y. So how would we do that? So f of y, which is going to be a function of y, is going to be the integral across the x domain, so 0 to 1, of f of ty dt. So that is going to be our marginal probability function for y. And again, if we integrate this function along the y domain, so 0 to 2 of f of y d, and we have to change the variables again, let's call it s ds. Notice that the area under the marginal probability function y is also 1, so it is, of course, also a univariate probability function, as we should expect. So for this two-dimensional curve, the x value should have a mean and the y value should have a mean. And you can calculate the x value, the mean x and the mean y, from their corresponding marginal functions. For example, the expected value of x can be found by integrating across the x domain, 0 to 1, I'll use capital T since I've already used T in the definitions of our marginal functions. So T times our marginal function of x of T dt. So that's the mean of our x value. And then let's look at the mean of y. So expected value of y, that's going to be equal to the integral across the y domain 0 to 2 of t times our marginal function y of t dt. And that, of course, gives us the mean value of y, right? So obviously the expected value of x is greater than the median, or possibly, I'm not going to claim that the median is equal to 0.5, but the mid-range is definitely 0.5, right? Because it's from 0 to 1. And the expected value of y is greater than the mid-range from 0 to 2, which is, of course, equal to 1, right? So if you had some software, possibly you can talk about some skewness, maybe, but we're not going to get into it there. But you could also calculate, for example, the second moment, the variance, and the standard deviation of x and y via these two things, and maybe even consider or analyze whether these variables x and y are independent from one another. So that is just an introduction on how to do some of the basics and fundamentals of integral calculus in the Desmos platform. So I hope you enjoyed this video, and I'll see you in the next video. Take care.